are looking at the complete carbon budget of locked forests and old growth forests. And we are particularly interested in looking at how the carbon comes in through photosynthesis. And then the trees use part of the carbon to make new tissue. So they make new leaves, wood and roots, and they use the rest of the carbon in their own respiration. And another form of respiration from the ecosystem is the respiration of the heterotroph. So that is like animals, microbes, so bacteria, fungi are breaking up the old carbon from soil and from leaf litter. So we're measuring the diameter of the trees. We are doing that repeatedly to see how much they grow. We are monitoring the litter fall by having live leaf litter traps. Then we got this root ingrowth course, which we bury into the soil and pull up every 3 months and look at how many new roots have grown into the core. We also have a flux tower, so it's automatically measuring about the forest. So it's recording for every 30 minutes whether that forest was a carbon sink or a source during that 30-minute period, and that's continuous, so we get an idea how the carbon source and sinks vary within one day, but also between different seasons, so when it's wet or dry. So when we analyze the data, one of the challenges is that the data is really coming in from multiple different types of measurements. So for the trees, we can measure all the trees within 1 hectare, but for the litter fall, we could never collect the whole hectare, so we need to just have some kind of sampling and how that matches up. Then they have different temporal resolutions, so litter fall we need to collect frequently because litter comes down quite fast, but the tree growth we can't go and try to measure each week because our resolution is not good enough. We couldn't see the difference in the tree size so quickly, so that we only do like once a year, and the roots we collect every 3 months, so that is one of the challenges of matching up all these different temporal patterns. So one of the very interesting outcomes so far is that the lock forest and old growth forest are actually equally productive. So people often think that locked forests, because they're younger, they are more productive. But actually what we found is that they do produce more wood, so the trees are growing faster, but because the old growth forests actually produce more leaves, so then actually that balances out. So the total productivity is actually quite similar. But then there's the difference in allocation, so locked forests allocate more of the incoming carbon into woody tissue and less into leaf tissue. From a conservation perspective, it's good that the locked forests are as productive as old growth forests, so they can capture CO2 from the atmosphere. So that's really important. Also, one of the important implications is that we shouldn't just be focusing on just measuring tree growth as is typically done, because it's quite easy. You just mark your stems and always go and measure at the same height, and then that would actually give us a false idea that locked forests are somehow like we would get an overestimate of their productivity because we would be ignoring the leaves and the roots. SAFE project is very unique in the sense that most of the carbon cycling studies concentrate on intact forests and not human-modified forests, because the intact forests are very important in the global carbon cycle because they are one of the biggest carbon sinks of the world. But we need to remember that there's an equivalent area or even more area of human-modified forest than intact forest. So if you want to understand forest as like a tropical forest a biome, we do need to have data from modified forest as well. And this type of selective logging and salvage logging is quite typical management of the forests. But yet we don't have any data from the carbon cycle from these forests except what we have been collecting from SAFE now. So we think, to our best knowledge, these are the first estimates of a modified tropical forest carbon budget that we have from anywhere in the world. So another key result that we have found, so we have found a similar productivity in locked forest and old growth forest, but the locked forest have a higher rate of carbon going out. That is because there is more heterotrophic respiration. So what that means that there is more carbon decomposing. So it's coming from dead wood and from soil organic matter. And we think that is the legacy of the logging, because during logging quite a large proportion of the logs get left behind because they are not suitable for timber. And also because logging creates a collateral damage. So the trees that are actually not felled, they might die because they're damaged, and also because the gaps are then colonized by pioneers, which have a shorter lifespan. So we have more tree mortality. That means that we have more dead wood, and that means that we got more carbon fluxes as the decomposition rates are higher.